This video is going to walk through how you might go about setting up a metal-insulator-metal metamaterial perfect absorber in COMSOL Multiphysics and then model it to look at what the absorbing spectra actually looks like. In a minute, I'll explain exactly what I mean by a metal-insulator-metal metamaterial, but predominantly we're going to be looking at how to apply that and create that in COMSOL Multiphysics. Now, I will note that many of the ways that I'm going to accomplish these different tasks, making the geometry, making the mesh, setting up the model, all of those things, many of them have more than one way to do it. So look at this as just an example, a way to get started and get some reliable output. And then in future videos, I'll talk about some variations and things that you might change and why you might want to do that. This is a unit cell for a metal-insulator-metal perfect absorber. And so what you're seeing here is a metal cylinder structure, so kind of either a rod or cylinder, however you want to think about it, and a metal layer on the bottom, and they are sandwiching an insulator layer. For our perfect absorber today, we're going to use aluminum as the metal, and then aluminum oxide, or Al2O3, as the insulator film. So this looks like a kind of strange structure to use on its own, but in reality, you use a lot of these. It's a periodic structure, and so it repeats over the surface of your sample. And the idea here is that when light interacts with this material, the wavelength of that light is going to be much greater in size than the period of the structures, so both the size and how they are spaced apart from each other. Because of that, the light basically sees this as one material or an effective medium. And so by designing the circle structures, the columns just so, we can kind of change what the effect of that effective media actually is. And this is how we can tune what wavelength we're interacting with and how well we can absorb that wavelength. So when you open up COMSOL Multiphysics, you'll see a screen that looks like this. There's a model wizard button over on the left and a blank model version. For the moment, especially as you're getting started, I recommend starting with the model wizard and going through and selecting your geometry. Anytime you're doing a simulation, it's always wise to think about how you can simplify or reduce what your system looks like. That will help you set up good physics and actually make sure it works in a reasonable amount of time without having to spend a lot of time troubleshooting. In this case today, because of the structure we're working on, I'm going to start with the 3D dimension. Then it takes us to the Select Physics page. You can see what I've been up to lately up here and recently used, but if you haven't used any of these models before, these are the particular physics equations and approaches that COMSOL is going to use. So it's good to pick one that is close to the situation that you are actually looking at studying. In our case, I am looking at optics. And within the small kind of metamaterial world, I also want to stick with the wave optics rather than the ray optics. Ray optics might be appropriate for a geometrical lens, so a larger kind of macro scale lens. Wave optics is more for antennas or smaller structures like photonic structures or metamaterials. Within wave optics this time, I'm going to pick the electromagnetic waves frequency domain. And I can just click that. I can either double click it or I can click it once and click add. It will add it to our physics interfaces. At this point, you can add more than one kinds of physics, depending on what you're trying to accomplish. For this tutorial today, we're just going to stick with the electromagnetic waves. And I'm going to leave all of the dependent variables at their defaults. So from there, I'll go on to study. And here you can either pick frequency domain or wavelength domain. We're going to be working in the red to near infrared, so kind of at the edge of the visible spectrum going into the near infrared. In that range, personally, I like to think in the wavelength domain. It's a little bit easier for me, so I'm going to use that for my default study. You can also do frequency domain just as easily, and of course, using math, because there's a relationship between wavelength and frequency, you can actually flip back and forth between them if you decide to that you need to make a difference or make a change between the two later on in your model. But for the moment, I'm going to stick with wavelength domain. I double clicked on it, and so it will automatically select that and move on to the next thing. So here's the main COMSOL interface that we'll be dealing with. And as with many software systems like this, there are multiple ways that you can navigate through the various steps. The way that I like to think about it is basically going all the way down this this ribbon up top. And we did a couple of steps already in that we added a component because we went through that model wizard. We added a component element here. We'll get to the parameters in a second. Here we'll talk about how to make the geometry or set up the geometry. Then we'll apply materials to our different components. We already added in the physics for this particular model, but if we decide in the future that we want to add physics, like maybe look at how heat is developing or existing within our system, we could do that. Then we'll build a mesh. I'll talk about what that is later on in the video. And then finally compute. Once we run compute and have all of our evaluation data, we can then manipulate that data or do different things and look at different ways to set up graphs that will be descriptive and give us information about what is happening in our structure. Now, all of these things you'll notice also appear over here in the model builder. So we can also use this window in order to navigate between our different components. Similarly, you can click on the different titles up at the top. So if you see me click something different and you get confused, feel free to go and use which component is most natural for you, whether that be the ribbon or working completely in the model builder or the file headers up top. So to start, because we have a component, I want to create a geometry. If you open this little window, we don't have anything here yet. And so I'm going to give it a name. I'm going to say this is the unit cell because our metamaterial has a unit cell that is going to be our basic structure that will then be repeated over the rest of the surface. For unit length, I'm going to move down to nanometers because that is the most typical scale for the types of features that we'll be talking about. And that means the nanometers will be the default for any component we built within this component one here. So now I'm going to go over here to geometry and pick block. Nothing showed up in the graphics over here, so we can't see anything at the moment because nothing is built. It does pre-populate with some different variables. So right now our block, if I were to hit build all objects, it would be 1 nanometer by 1 nanometer by 1 nanometer. So 1 nanometer cubed. And that's what we see here. 1 nanometer on all 3 sides. Really, all 4 sides, I suppose. In our case, we don't want it to be that small. Not only do we not want it to be small, we also honestly don't want to have to change it in this particular menu because we might have these sizes exist in other layers of our structure. And so we want to parameterize or turn this into a variable. So what I'm going to do is call this one unit W because that's going to be our width. I'm going to call this unit L. You can also call it unit depth if you wanted to. But that's going to be our depth. And then for the height, this is going to be the thickness of our dielectric layer. So I'm going to call that di T, so dielectric thickness. Now, the red lines underneath the bottom tell us that COMSOL has no idea what these things mean. And that makes sense. We haven't defined our variables yet. So now we'll go back to parameters 1. And this is where we can define all of those things. So now if I say unit W, maybe I want that to be about 300 nanometers. And this is going to be the width of the unit cell. We can define the rest of our variables in a similar way. In this case, I want a square unit cell, and so I'm going to set unit L equal to unit W, and you see the value changed accordingly. And then for the thickness, right now I'm going to do about 80 nanometers just as a starting point. And this is going to be thickness of the dielectric layer. Now, these are not the only dimensions that we have in our metamaterial unit cell. We will also have that top metal thickness. So I'll set that here. Say equal to 50 nanometers for the moment. But that top metal layer is also going to be in the shape of a cylinder. It's going to be a circle with some height basically that we just set. And so I'm going to give that a radius that I can use later. Since our unit cell is only 300 nanometers wide, I want to make sure that my radius is less than 150 nanometers so that my circle in the end doesn't end up bigger than my unit cell as a whole. So for the moment, let's do 100 nanometers as the radius. And then finally, we will want an air column above our structure. And so here, I like to make this dependent on the target wavelength that we are going to be using. So I'm going to make a lam, or short for lambda, variable here that I'll define here in a second, and multiply that times 3 as a starting point. I always forget to define lambda first, so I will do that now. Let's say that our target wavelength is going to be 600 nanometers, so it's kind of in the red. You'll notice that the air column or the air block height changed once I set that lam variable. So yeah, the reason I do that is we want to have a port later on. So we're going to have a place where light comes in, interacts with our metasurface, and then will bounce back out. And so we will collect information both for the input and the output at that port. And we want it to be several wavelengths away so that we get that far field effect, because in our case, for this particular application, we are wanting a far field effect. If you wanted to look more near field, maybe you wouldn't need to worry about this. But for the moment, we'll keep it there. And so these are all the parameters that I can think of at the moment. If you wanted to save these so that you could use them again later, you might save them off into a text file, and you can do that or make as many as you want. That's also fine too. If we need to add more later, we can also do that as well, but I think this is enough to get me started. So I'll go back to block 1, which I'm actually going to name electric layer, and leave it at that. So now that we have some size to our object, I can build all objects again. You notice now it's way bigger than our screen allows us to see. So I'm going to use this button up here, zoom extents, and that will zoom out until the object fills the screen here. And that basically completes our first component. Now, right now I'm using the corner as the position, so it is basing all of these dimensions, including the different widths and things, in reference to 0 as that corner down there at the bottom. If you want, you can also use the center instead, and so if I change that, now it's going to move, and we're going from negative 150 to positive 150 nanometers in the X direction there. The axes for your reference are down here in the corner. It doesn't really matter, it just mostly changes how you set up some of your equations later on. For the moment, I'm going to go back to corner just because that's what I want to use right now. Okay. So I told you earlier about how you can use these buttons up here to add your different geometrical components. Well, another way to do it is to right-click on your geometry, and you can see that there are even more structures here. This is also under the more primitives menu over here up in the top ribbon. But right now I'm going to create a cylinder. And as we defined earlier, I'm going to make the radius variable from before, and the height, the thickness of our metal layer from before. For the position, this is where some of those other parameters can come into play, because for the moment, we're going to stick the cylinder in the middle of our square, but maybe in the future we wanted to move it somewhere else. Well, we don't have to hard code in the numbers for this position. We can make them all in reference to both our 0 point, which is our corner, and also the dimensions of our square, so our parameters that we've set. So in our case here, the x, the midpoint of x, is going to be halfway up the unit cell width, right? And so we can make this unit w divided by 2. And because we used our 0 at the corner here, then we can just use that positive value. Same thing is going to be true for y. Now for the z, we want it to be above this dielectric layer thickness. And so we'll need to make sure to use the thickness there, because the position is for the bottom of our cylinder. It's not for the middle, it's for the bottom. And so we'll build all of that. And we have a beautiful little cylinder. I'm going to rename that just so we can see it over on the left-hand side over here. You don't have to rename these if you don't want to, if you're iterating a lot of different things and just trying out some different structures. Honestly, I don't typically change the labels, but it does help for readability later on, especially if you're going to be passing this model on to somebody else. Okay, for the last thing that we need, I'm going to make another block. Dimensions in kind of that XY plane are going to be the same as before. But the height now is going to be our air height. And that's because this is going to be our air block. So if I build that, build selected, now we have this giant rectangle. It's huge. So this is why setting the air block to some factor of the lambda, or of our target wavelength, is helpful, because we can change pretty dramatically the height of this cylinder. Maybe getting 2 wavelengths away gives us that far field behavior that we want, then it's pretty easy to change that multiplier. But you can imagine if this block is too large relative to that wavelength, then your calculation is just going to take a little bit longer, because the larger the volume, the more calculation points. So making it relative to that lambda helps it scale depending on what wavelength range you are trying to interact with. All right. Now that we have our air block, you notice we can't see our cylinder underneath. And so I'm going to go over here to the wireframe rendering, click that. You can see that here. That's one way to look at it. Or you can also look at transparency, and now you can kind of see the 3D structure, but now you can actually see the sphere in the middle. So with that, that is our geometry. Now we're ready to add materials. I already have the Add Material menu open because it defaulted to that for me based on the last time I was interacting with COMSOL. But as always, you can go here to Materials and Add Materials, or from the Home ribbon, you can add the materials here using this button as well, or you can even right-click over here. So there's a million different ways to get there, but it all opens up the same menu over here. Now, again, for me, I can go to recent materials and it will bring up a lot of the materials I'm looking for right now. But if you want to find them for the first time, I would always recommend going to the model that you, or the kind of physics that you are currently using. So for us, that's going to be optical, and looking within these available options. I recommend this mostly because it's going to have the kinds of parameters already preloaded that you're going to need. So for optical materials, it's going to have those N and K values. Whereas for liquids and gases, probably not going to have the N and K values, but it'll have things like viscosity, right, which is more relevant. Or for like semiconductors, it'll have things like mobility. So it's always good to start with these kinds of things. Now, it doesn't mean you can't change any of those parameters, because of course you can. But again, this is just for a good starting place. So first up, I want to find some aluminum oxide. So I'm going to look at the inorganic materials. And actually, since aluminum is here, I'll just open that up. Not a whole lot of options for me when you look here, but always remember, anytime you see this little caret arrow, you can open that up as well. So let's look at some experimental data. You'll notice in here, there is not aluminum oxide, but there is aluminum. In fact, there's a bunch of options for aluminum. So for the moment, I'm gonna pick an aluminum layer because I know that that is something that I want. The only difference between all of these options is really the reference that they're taken from. And so biggest thing that I look for is what is the wavelength range that I'm interested in and which material actually covers that range. So if we're looking at about the 600 nanometer range, that's our target wavelength, I'm going to find something that has 600 somewhere in the middle. So like one of these two options is probably good. I'll take this one right here. You can double click it, which is what I'm going to do now. Let's double click with the left click, and now it shows up under our menu over here. By default, the first material that you click automatically gets applied to everything in your geometry. I say when you're picking out your materials, don't worry about that for now. We can reassign things later. Let's just go collect all of our materials that we need. So we're looking for aluminum oxide, not in here. Well, where it's hiding is down actually with the oxygen. So oxygen and oxides. So that's the key word there, oxides. Got our oxygen, so just pure oxygen there, but we want the thin films. So here are several different options for the thin films. These are going to be largely crystalline thin films. So you'll want to double check the references if it's really important that you have a particular structure that you are targeting. For the moment, I am going to stick with these thin films, not the quartz. And I'm going to do the same as before, where I want to make sure we have coverage of the wavelength range that we're actually interested in. And so I will go with this one. Again, I'm going to double click and it shows up over on the left. All right, and that is it for our solid materials. The one that I want next is air. And so that should fall under miscellaneous and under mixed gases, because guess what? That's what air is. Whole bunch of different options here. Again, feel free to check the references if you have particular needs, but I'm just going to take this first one and start with that. Now that I'm done with materials, I can exit out and go back to zoom extent so I can see my whole structure. And when you look over here on the left, you'll notice even though I've added these additional materials, the aluminum is still applied to everything. And these other materials down here have that little kind of hazard sign down below with an exclamation mark. And this is just a mark to tell you that not necessarily that anything is catastrophically wrong, but that nothing is currently selected. This material is not used. And it could run this way. So we could run the model like this. But that is a good flag that, hey, this material I wanted to use, it's not being applied at the moment. So where I want to apply this is going to be our bottom dielectric layer. And so I can click on that aluminum oxide and then just click the region that I want to apply that to. That's going to be the bottom there. And so once you've done that, now when we go back and look at aluminum, our first region is overridden and that bottom region is no longer blue to indicate that it is currently being applied as aluminum. So we'll do the same thing for air here. Click that. Now it looks like that cylinder is blue, but it actually isn't. If we go click on aluminum again, that cylinder is still the only thing that's blue. Now, if for some reason you added in maybe aluminum oxide first, and we needed to reassign that cylinder in the middle there, you'll notice when I hover over it, the big rectangle here highlights green, meaning if I click on that, it's going to turn that particular structure on and off, which is not helpful. We want that to be air. So that is accurate right now. Well, if you mouse over the other structure, so our little cylinder here, and then use your mouse wheel, it will allow you to select other structures within the geometry. And so, in fact, if I keep on kind of scrolling through, it will highlight all 3 different ones in turn. And so that's how you can select that cylinder, even though it is currently being kind of overrun by the air block right now. So I'm going to actually deselect that because I don't want it to be air. But with that, we have an aluminum cylinder on an aluminum oxide base, and then we have an air column. Our materials are now all set, so we move down to the next thing, which is our physics model. I know I said that we have set this up already, but really that just means that this is the physics that's being applied to our geometry. We haven't set up the specifics of how that physics is interacting within our geometry. So there's still a lot of changes to make. Again, we can go down here, we can click up at the top to change different things. So by default, when we click on just that electromagnetic waves frequency domain, you can see the equations here that are being applied to this whole geometry. So this is showing an equation assuming the first study, which is the only study we have right now, and we want it to be study controlled. There are other modes, but for the moment, we're just going to stick with this one. Again, we're going to stay with all of the defaults for this, but these are all settings that you can dive into and learn how to use as you begin getting more familiar with COMSOL. The wave equation is going to be applied to this whole geometry. That makes sense for us because that's the only model, that's the only physics we're using right now. In other scenarios, there might be cases where you're applying an electric field or maybe current as like a circuit or heat or something like that. And maybe you don't want the wave equation to be calculated everywhere in your geometry. Maybe you just want to apply electrical current somewhere. And so this is why it can specify where you're applying that wave equation. Right now, everything is a perfect electric conductor. That is not accurate. That will not remain the same. But the thing that is important to stay as a perfect electric conductor is actually this face on the bottom. So down here, which it won't let me select it right now. Oh, hey, there we go. Number 3, we want that to stay a perfect electric conductor. So the reason for that is in our metal-insulator-metal metamaterial, from this point and further down would actually be another metal layer. Realistically, that metal layer would be opaque, meaning it's relatively thick. And so rather than modeling that as a really big square, really big rectangle that we then have to calculate a whole bunch of different points at, it is a reasonable approximation to call that a perfect electric conductor. So we're just going to say that it is a perfect metal. Now, that will technically change our results a little bit, but again, it's a really decent starting point that allows us to reduce the calculation time involved in this model. So that one we will want to stay the same. Now, in terms of the other interfaces, let's start off with adding a port. So this is going to be our input. And we will be exciting and adding a wave excitation at this port. So that is going to be our top interface up here because we will have light that is coming down, interacting with our metamaterial, and then coming back up and being collected. Now, because this is a periodic structure and we're only really looking at a single unit cell right now, we need to employ a periodicity element or condition to this structure. So rather than using a user-defined port, we're going to use a periodic port. In this periodic port, we can, well, really in any port, but especially in the periodic ones, we can specify what direction our electric field is pointed. In this case, with our circular structure, we don't care a whole ton. We mostly want it to be in that XY plane. So for the moment, I'm just going to put it as 1 in the Y direction. It's mostly going to be in the Y direction. But you can also change it to be specify for the magnetic field, or you can put it in the Z direction. Basically, changing all of these things just tells you if it's a TE mode, TM mode, or what kind of orientation that electromagnetic wave is. Additionally, you can change the elevation angle of incidence. So this is what we would typically think as the angle of incidence. What is our angle with respect to the normal of the plane? So if perpendicular, perpendicular to that input plane would be 0 radians angle of incidence. Whereas if you were just kind of very barely skimming across the surface, you're basically parallel with the plane, that would be 90 degrees. Couldn't tell you what that is in radians. I'm sorry, I forget. But that is another thing that we can calculate out. So what we can do is set this as another parameter. I'm going to call that angle in. And then this azimuth angle of incident is basically rotation within that XY plane. So I'm going to call that rotation in, just so that I can keep them straight. And then we'll go set these as parameters. In, I'm going to make that 0. I'm going to specify degrees because, again, that's how my brain personally thinks best, is in terms of degrees. And the nice thing is when you do that, is COMSOL will automatically change it to radians. So yes, okay, 0 degrees is 0 radians. Yes, that's not exciting, I understand. But if we were to make this maybe 45 degrees instead, it will automatically calculate the radians for us. And I'll add this other one. Again, I'm going to say 0 degrees there. Anytime you are changing the units or want to dictate the units, you want to make sure that those are in square brackets, and then COMSOL will automatically calculate out the units that it needs for its calculations. This is really nice because you can use whatever you are most comfortable with, and then COMSOL will also use whatever it is most comfortable with. Everybody's happy that way. Let's go back to the port. We've got that. You can also change the incident phase if you like, or we can do things like the automatic diffraction order calculation. For this initial study, I'm not going to worry about that diffraction order, but you most certainly can later on. All right, so we have our port, we have our periodic condition set. Now we need to tell it what boundaries it needs to be periodic on. How is our structure being repeated? So I'm going to right click on the electromagnetic model and select periodic condition down here. The reason why the icon next to periodic condition and the port only has, I guess, really one interface that is blue compared to the whole thing is because this only applies to a boundary. The wave equation, the electric wave equation, is entirely blue. It's got a little D next to it because it is a domain, meaning that encloses an entire volume. When it's just one interface that is colored in blue, that's a boundary, so that is going to be a plane. And then, of course, you have points or edges as well. So for this, the type of periodicity we're going to use is the Floquet periodicity. This is a really common approach, is just a specific mathematical approach for looking at periodic structures like metasurfaces. For that K vector, rather than using user-defined, I can make it just from that periodic port. So everything stays self-consistent. To select which sides of the structure are in this periodic condition, I want to first select all the interfaces on one side of my structure. So in this case, it is the edge of my dielectric and the edge of the air block. And then I also want to select the opposite side. So the large air block and my dielectric. And it will automatically, COMSOL will automatically set that up as sources and destinations. Now this is only for two sides, right? So I want to make a second periodic condition for the other remaining sides. And so now when I look at our structure, I have it weirdly rotated. So I'm going to both do that and then have it reset. There we go. We can see the far two sides are selected for this periodic condition, and then they flip to the other ones when we flip back and forth between them. So now we have our periodic conditions. We have set all of our side walls to a particular condition. We've set our top to the port, and now if we click that perfect electric conductor, we still have that bottommost plane selected there. And so everything is looking good so far. Now that we have our geometry and our physics all set up, we are ready to create our mesh. So the mesh is the creation of points within our volume at which calculations are made. So everywhere the lines intersect and everywhere we have a node, that is going to be a location where COMSOL uses our electromagnetic wave equation, as defined here, and makes a calculation. And that is going to be based on inputs from multiple directions into that node. And assuming those calculations are within some error boundary, then it will move on to the next condition. Of course, it does it much faster than that sounds, but that's effectively what's happening. And so in this mesh, it's very frequent to just leave it as physics controlled. This will adjust based on the particular kind of physics that you are using, but it still does give you some customization options. So for example, if we have normal size here, we'll go ahead and build all. These are relatively big structures. We can make them finer, which gives us more mesh points, more calculation points, and increase the density a little bit here. For the moment, this is the maximum mesh element size is coming from the study, which is fine. But our study wavelength is set at 1 micron. And so that's why these structures are so large. Now, if you remember, our target wavelength is 600 nanometers. So instead of that, we want to set this for the moment. We will change this again here in a minute to 600 nanometers. And then I'm going to go back to my mesh. If we build it again, now all of our structures are a little bit smaller. And so that is to adapt to that smaller wavelength. This is one thing that you can definitely micromanage. You can go in and use the user-controlled mesh that gives you a variety of build settings. I will say if you are a newer user to COMSOL that can get overwhelming very fast. So as much as possible, just stick with the physics-controlled mesh and adjust to coarser or finer mesh as necessary in order to get your calculation to converge. We're now ready to finalize our study so that we can actually run and get some calculations. So to start off with, we don't want to look at our absorption spectrum at just a singular wavelength. Typically, we'll want to take multiple wavelengths worth of information. And so using the range button on the right-hand side in our settings window is helpful. I'm going to set our starting wavelength. Now you notice it's in terms of microns. I don't love that because we're mostly going to be dealing with visible and near infrared. And I like to think about those in nanometers, so that's what I'm going to do. And so now that has changed over here. I can start at, let's start at 500 nanometers, go in steps of, let's say, not 120, 10 nanometers, and then let's stop at 700 nanometers. This is a pretty small range. But when you're running a simulation for the first time, it's better to keep things nice and narrow with relatively bigger steps, just to make sure you've worked out all the kinks in your physics model. So here, because I had something in the wavelengths box already, I'm going to hit replace, and it will automatically replace that with the code required to set the range I just set up. Another thing that I like to select is this reuse solution from previous step, especially when you're doing wavelength-based calculations, because this uses the previous step as a starting point. So it just makes your calculation run a little bit faster, makes it more likely to converge if you've got weird behavior going on. It just makes it a little bit easier. And yeah, so let's just stick with that for now. We are ready to compute. And here are the automatic things that it spits out for us. So first up is the electric field. This consists of multiple cut planes that allows us to see that electric field as it comes in and out. And so I'm going to turn that a little bit so that we can see the enhancement at the edge of our metal layer on the top there. And this is sitting at 700 nanometers right now. You can change this here, so maybe we want to look explicitly at 600 because that was our target. We'll look at that here. And you can see we get a little bit more reflection, actually. The nice thing is up here up top, you can actually cycle through the different settings. So you can see the lambda changing up here. Looks like we're actually getting absorption at some of these lower wavelengths. So we'll have to go check that out here in a second. But it is a nice way to just cycle through and see what's happening in your structure real quick. Now, this reflectance graph is really what we care about. So reflectance gives us, of the light that comes in, how much actually makes it back to that first port. And so we see a major dip down in the bottom at 540, and then it goes up to about 80%. This may not be all of the information that you want. Maybe you want to see the absorption, reflection, and transmission of your device. Well, for that, we're going to have to make a new plot. So we'll click on the results here. And again, you can either right click or you can go up to results, and we're going to add a 1D plot group. And I'm going to call that ATR, absorption, transmission, and reflection. You can mix that acronym up however you like. But within this 1D plot group, I'm going to make a global plot. That'll add a subset down here. And now in this x-axis data, we can add different expressions. This is where the variables for COMSOL come into play. If you have the manual up, you can look up what those are, but you can also just add them. Here we have a button for replace expression. Here we have add expression. And so let's go ahead and do add. And we can look within our specific model, in this case, the electromagnetic waves model, and click into ports. And these are the things that are calculated at our ports. So we can look at reflectance by order or port name. You can look at the S parameters, if that's how you prefer to think of things. In our case, I'm going to go ahead and take our absorbance measurement calculation and double click on that, and it gets added in here automatically. Then I'm going to add again, go down to ports and say the reflection. So that's our total. I'm going to add again, down to ports, and do our transmission total. All of these things, or all of this basic same kind of format, is how you can pull in variables from any kind of model. And again, I'm kind of skipping around a bunch of other ones. You have impedance and energy and other polarization state information. So there's a lot of things that we're not touching on right now. But you can pull these in, and you can also do calculations with them so that you're not confined to just the expression, just the variable that comes directly from COMSOL. You can actually do things like absolute value or, just basic mathematical functions. This is plenty for me right now, though, so I'm going to leave it there. On the x-axis data, parameter value is fine, and that should be in terms of nanometers. And that is the resulting graph that we get. So, as anticipated, we have a absorbance peak that happens at 540 and then goes down. We still absorb a little bit, but not nearly as much as we do at 540, which honestly, pretty good for a little metal structure on top of basically a mirror. we'll take it. But this is still happening at 540. And so maybe we want to adjust some of our parameters in order to see if we can push that peak all the way over to 600. Well, what do we do for that? For that, we'll have to go back to our study. And instead of changing study 1, we will want to add a parametric sweep. Within this parameter, we can sweep a number of different variables since we parameterized all of the conditions around our geometry and our target wavelength, all of those things. So in our case, the thing that makes the most sense to adjust is the radius of that top cylinder. So I can select that, and then much like the range value with our wavelength from before, I can click on our parameter value list and have COMSOL help me set up a range for those values. You can stick with step, but here maybe you want number of values. So maybe I want to do 5 different tests, something like that. And so I maybe want to start at 60 nanometers radius. It's very small. 120 nanometer radius. 120, not 112. And let's do like 6 values. I want to do 6 different radial values. And so I'll hit replace for that. And again, it automatically sets up that function so it can do the correct steps for me. You can add multiple different parameters. I will say if you add multiple parameters, so say we want to change the angle of incidence to be 0 radians, 45 degrees, and 90 degrees, something like that. The way it's set up now, it will only do a specific combination of these 2 parameters. So it basically look at this array and look at this array and do a 1-to-1 kind of combination. That's not what I want. I want to do all combinations of these things. And typically COMSOL will fix the bottommost parameter first and then sweep the next one. And we'll kind of do it that way all the way up the list. And so I want to put the angle of incidence last down at the bottom, my M radius up top, and then it will still, because of my wavelength domain, it's sweeping this range of wavelengths, it will still sweep that as well. So I can go back to parametric sweep and hit compute, and I'll be back in a minute when that completes. Now that my simulation is finished, we've opened up to the screen that you see here. You'll notice everything is a 0, which initially makes you go, oh no, it didn't work. But something to keep in mind, remember that our angle incidence, or incidence angle, we did a sweep, right? We did 0 degrees, 45 degrees, and 90 degrees. Now here it says in radians, we have 1.57 radians, which is in fact that 90 degrees. And so this is where the input wave is parallel to the surface. So it's not actually even interacting with our material based on everything, the orientation of everything. So it makes sense that nothing interesting is happening in this condition. If we move to that 45-degree angle and replot, now we're getting something. So something interesting is happening. Now again, this is the electric field, so maybe not the most interesting thing for us on the planet. We want that reflectance. So let's click down here on our reflectance, and initially it looks like a big mess. There's just a whole bunch of blue lines, but the fact that we see these diagonal lines tells me that COMSOL is plotting this graph like it is one continuous line, not a whole bunch of different data sets. And so fixing that is relatively easy, even though, again, it looks scary to start with. But we'll go down here to global, click on that, and your culprit is down here in the x-axis. So right now, the source data is all solutions, and that's not super helpful for us. We want to do it by lambda naught. So lambda naught is the default COMSOL variable for whatever the wavelength is. So this is the variable that is changing as our wavelength is being swept. And so if I click on lambda naught, the expression is that the unit is still going to be nanometers, although here you could change it to microns if you so desired. I can click back on reflectance, and now we have a bunch of individual lines. Of course, the legend makes it impossible to see, so I'm going to scroll down to the legend and hide that for a second here. Do in fact have discrete lines, so yay. For the sake of thinking about how our metamaterial actually behaves, I'm going to pick a particular incidence angle. In fact, I'm just going to go with 0 for the moment and plot that. If I pick 0 angle incidence, this is what they all look like. If I pick 45, which is what we were originally testing for, this is what we get. And so we still see the dip down in the reflectance that we saw before, but you notice that that dip, where that dip happens, shifts as our structure in our metamaterial gets larger. So it shifts towards red, so it redshifts as the structure gets larger, which actually makes sense with how these things behave. A couple of things that we can change. First of all, we can move the legend around using the different options down here. We can make the position down in the lower right, which would help a lot. Have to hit replot after that, and that just helps us to be able to see. The other thing is, as before, we don't necessarily care about reflectance. So if I wanted to make another plot, which I still can, go here and hit results, another 1D plot group. We're going to make this absorption and change the study to our parametric solutions because that has the big data set that we just made. And now I'm going to add a global plot and specifically add in our total absorbance. Our x-axis data is already lambda naught, so it should automatically just show wavelength. And if I click back to the main absorption option, then we see our maximum absorption. Again, it defaults to showing you as much data as possible, and so that makes our legend a little bit a problem when it comes to being able to see things. So I'll put that down and go ahead and pick from list and say our second one there and plot it so it looks like that. So we get the best absorption around 530 when our radius is about that 96 nanometers. And that feels like a really weird size, but that's just because of the step sizes that we chose. Now that we have an idea of where the peaks are and what kind of shifts we can anticipate, we can change what our different ranges look like so that we can maybe optimize for closer to 600 over here. So here we're at about 85% absorption. If we wanted to be a true perfect absorber, we'd want to be closer to 100. And so maybe we would adjust the thicknesses or the size of our unit cell and make some more calculations to get closer to that ideal. If instead of seeing a plot like this, we wanted to have more data in terms of maybe a heat map, how you would do that is click on derived values, specifically do a right click on derived values, and go to global evaluation. Click on that. And so in the global evaluation, this is the expressions of what we actually want to calculate. In our case, that is going to be the absorbance because, again, that's what we're looking for. We want a perfect absorber. We care about absorbance. And so I'm going to go down to the study that we actually ran with all of our parameters and click evaluate. And that will create a table with all of that absorbance data. Once we have that table made, we can either plot just a graph from that table itself, or we can make a surface out of it. And so this surface allows us to plot basically two different variables on our different axes, and then use the color as a way to show that value that we just calculated. So our absorbance in this case. So the color scale shows us the absorbance, and then we can change which things our two axes actually are showing. So here I can click on the table surface and it does show, you know, these different things where the information's coming from, what table it's coming from, so on and so forth. The plot data, when it says from table, it would just automatically pick a couple. But if I make it manual, all of these options all of a sudden become available to me. So Personally, I like to make my x-axis be lambda, and we can keep the y-axis data as that radius, and then just look at the absorbance and then hit plot. And now we can see where we get the kind of that maxima is when our radius is somewhere in here, although it looks very different. Oh, I know why. Because we are looking at an angle of incidence of 0. That would make sense. Let's go to this one. And yeah, that's where we go. So within here, we can see how as our radius of our structure gets larger, that peak is going to move. Now, because we only have a handful of radius sizes that we tested, this is maybe not the most robust and filled out heat map, but again, you could adjust those ranges and how many test states that you used in order to make a more complete and well filled out heat map. But this is a nice way to visualize a lot of data in a way that's a little bit easier to digest than a graph with a whole bunch of lines on it. So that is where we're going to end with this tutorial. As I mentioned, this is just one way to do a lot of these things. Look out for future videos in order to learn different ways to approach the same problem and ways to simulate other kinds of devices.